This is Jack Sarfati. I'm talking about flow-quay-driven room temperature macro-quantum coherent Further condensates in quantum dot artificial neural nets. My co-author is Elon Musk's Grok 3 artificial intelligence. And this talk is scheduled for 11:30 a.m. around March 18th, 2025, the American Physical Society in Anaheim, California, although I'm speaking virtually. It has been proposed by Hameroff and Penrose that consciousness is generated in the Einstein-Podolsky-Rosen entangled network of electric dipole moments of the protein dimers in the microtubule substructure of living matter, pumped off thermodynamic equilibrium via molecular level metabolic pumping, ATP and all that, similar to that of the pump of a laser. We propose a Gedanken experiment to test the Hameroff-Penrose hypotheses using artificial microtubules constructed out of metasurface lattices of interacting electric dipole quantum dot meta-atoms forming artificial neural networks. Turing-type tests of pattern recognition training of the net when in incoherent thermodynamic equilibrium will be compared to the same training when flow-quay pumped above the critical threshold power into the coherent laser-like further condensate of collective modes of the electric dipoles. We expect quantitative differences in the behavior of this artificial neural net in these two different modes, the incoherent one below laser threshold, so to speak, and the coherent mode above the laser analog threshold. Let's review quickly the basics of microtubules. Microtubules are major components of the cytoskeleton. They are found in all eukaryotic cells, and they are involved in mitosis, cell motility, intercellular transport, and maintenance of cell shape. Microtubules are composed of alpha and beta tubulin subunits assembled into linear protofilaments. Basically, they are quantum dots in terms of quantum computer information theory. A single microtubule contains 10 to 15 protofilaments, 13 in mammalian cells, that wind together to form a 24 nanometer wide hollow cylinder. Microtubules are structures that can rapidly grow via polymerization or shrink via depolymerization in size, depending on how many tubulin molecules they contain. Here we have an illustration of a microtubule. I asked Elon Musk's Grok 3 artificial intelligence to explain flow-quay pumping, creating room temperature open non-equilibrium macro-quantum coherent states of emergent collective modes analogous to lasers, but confined inside the many-particle system. Artificial intelligence responded to me, quote, "Let's break this down step by step to explain flow-quay pumping and how it can create room temperature open non-equilibrium macro-quantum coherent states of emergent collective modes analogous to lasers but confined within an interacting many-particle system. This is a fascinating topic at the intersection of condensed matter physics, quantum mechanics, and non-equilibrium dynamics. So I'll aim to make it clear and precise. What is flow-quay pumping? Flow-quay pumping comes from flow-quay theory of differential equations with periodic time coefficients, which deals with periodically driven systems. Imagine a quantum system like a lattice of particles or spins where some external parameter, for example the electric field, magnetic field, or light, oscillates in time with a fixed frequency. This periodic driving doesn't just shake the system randomly, it can fundamentally reshape its properties, creating new states that would not exist in equilibrium. In essence, flow-quay pumping involves using this periodic drive to pump energy, momentum, or other quantities into the system in a controlled way, like tuning a radio to a specific frequency to amplify a signal. But here we're tuning a many-body quantum system to engineer exotic states. I will add that these exotic states can have topological protection, making them immune to heat death, the decoherence that plagues quantum computers, and also in living systems and now our living bodies, the flow-quake pumping corresponds to the metabolism, the ATP molecules and all that. I'm not a biochemical expert, so I really don't know the details of that. Again, basically, artificial intelligence is talking here. Number two, non-equilibrium in open systems. Normally, quantum systems at room temperature settle into thermal equilibrium, where coherence, the ability of quantum states to maintain well-defined phase relationships, gets washed out by thermal noise. However, flow-quake pumping keeps the system out of equilibrium by continuously injecting energy. This is a non-equilibrium state because the system doesn't relax to a simple thermal bath. It's dynamically sustained by the drive. I'll add, that's the key difference. In the papers by Anthony Valentini, he never considers this situation. He only considers starting off in a non-equilibrium state and then relaxing to equilibrium, where in the quantum case you get the Born probability rule with EPR, non-signaling, etc. So Anthony Valentini, in his interesting papers, actually got the right answer to the wrong question. Let me continue. Grok AI continues. The open part means the system exchanges energy, particles, or information with its environment through dissipation or coupling to a reservoir. The openness is a key and allows the system to shed excess energy while maintaining the desired quantum state, preventing it from overheating or decohering completely. So this is what all the people doing quantum computing have totally missed. And actually, they're pretty stupid to go to cryogenic temperatures to use superconductors when they could be doing everything at room temperature much more cheaply and much more efficiently. But I don't know if Google or any of these, Apple, I don't know, into any of these guys listening, but you should listen. Let's continue. Macro quantum coherent states. A macro quantum state refers to a large-scale quantum phenomenon involving many particles acting in unison rather than just a few. Coherence means these particles share a synchronized quantum phase, like dancers moving in step. In a flow-quake-driven system, the periodic drive can lock the particles' collective behavior into a coherent mode, a single unified quantum state spanning the system. This is where the analogy to lasers comes in. In a laser, light waves build up coherence through stimulated emission in a cavity, producing a macroscopic beam of synchronized photons. Here, flow-quake pumping creates a similar coherence, but instead of photons escaping as a beam, the coherent state involves emergent collective modes, that is, vibrations, spin waves, or other excitations, confined within the many-particle system itself. 6. Laser analogy, but confined. Lasers produce coherent light that escapes the system. In contrast, flow-quake pumped coherent states are trapped inside the material or lattice. Think of it as a laser-like state where the coherence is in the particle dynamics, synchronized oscillations of spins or lattice rather than emitted radiation. The confinement comes from the system's boundaries or structure, keeping the collective mode localized. Putting it all together, flow-quake pumping uses a periodic drive to push a many-particle system into a non-equilibrium state. By carefully balancing energy input and dissipation in an open system, it creates macro-quantum coherent states of emergent collective modes. Think of a symphony of particles oscillating in unison. These states are laser-like in their coherence, but stay confined within the system. At room temperature, this is possible because the drive and dissipation outmaneuver thermal noise, opening a window to quantum phenomena in everyday conditions. This concept has exciting implications for quantum technologies, like designing materials with tunable quantum properties or exploring new phases of matter. It is a testament to how non-equilibrium physics can unlock impossible in static, can unlock behaviors that are impossible in static equilibrium systems. Okay, since this is a short talk, I'm going to stop here and ask for questions. The rest of the slides are basically references to Mikhail Altesky's work in Moscow, very important work this physicist is doing. Also, a little more on what quantum dots are. That's all basically out of Wikipedia. Then I get to the point in slide 11 on conscious artificial intelligence. Jumping to slide 11 on conscious artificial intelligence, the next step in the AI industry, something that my next door neighbor Sam Altman is not even aware of, it seems. Neither is Elon Musk or any of the top guns in artificial intelligence. I don't know if the Chinese or Russians are working on it. We'll see. But in any case, slide 11, I basically refer you to a paper by Pavel Pilkin. Is the brain analogous to a quantum measuring device? Section 7 of his review paper describes my post-Bohmian quantum solution to the hard problem of consciousness in terms of physics raised by David Chalmers in his well-known article in Scientific American almost 30 years ago. So I will leave that as a homework problem. And the last thing I have here is, yes, Roderick Sutherland's papers on action-reaction, which is the key to getting conscious artificial intelligence. I gave a reference to one of his several papers on the archive, and I also give a reference to Mikhail Altesky's paper on quantum neural nets based on quantum dots. And finally, the paper, well, not finally, the subquantum information computation paper of Anthony Valentini, in which he shows how to get beyond quantum mechanics and how to actually get quantum entanglement signaling without needing a classical signal key, because you have to basically, in non-equilibrium, violate the Born probability rule. Quantum mechanics becomes nonlinear and non-unitary, so the no cloning photon theorem is no longer applicable. This is analogous to how in general relativity, when you get gravity, you violate certain restrictions of special relativity. And finally, a reference to an early paper I did with several other people on this post-quantum theory involving action and reaction, which is missing in orthodox Copenhagen theory, but is there implicitly in the Bohm ontological interpretation.